Okay, now that we know integers and polynomials behave in much similar manner, we want to define a language to describe both of them at the same time while ignoring the differences. So what are common between integers and polynomials? First of all, we know that they both have addition and multiplication. So these are both binary operations. And also they follow some rules involving addition and multiplication, such as distributive laws and commutative laws and so on. So we abstract these behaviors to define rings. So here is the definition of a ring. So let R be a set, and we with addition and multiplication, the meaning of which we will define later. Multiplication. At this moment, addition and multiplication, they are just meaningless words. Okay, and for any elements a, b of this set R, the addition is denoted by a plus b. Okay, but this plus is not necessarily the same plus as in numbers. So it can be, it's just a symbol at this moment. Okay, so this is called a sum. And we also define multiplication, AB. Sometimes we write like a dot b or a star b or whatever. Anyway, this is another binary operation, and the result is called a product. Or we say product of a by b, b by a, or what? Maybe we should just stick to saying a by b. Okay, but these are just uh, meaningless notations at this moment, and we give some meaning by how they behave, by their behaviors. So first, we list axioms of addition. Okay, A for all A, B in the set, A plus B is also an element of R. Okay, so this means addition is closed within R. And B for all elements of ABC of R, we have A plus B plus C is equal to A plus B plus C. This is called associativity. And C. There exists an element, so a distinct element called 0, such that for all, okay, we write 0, which is an element. So this is a specific element in R, such that for all elements in R, we have a plus 0 is equal to 0 plus a is equal to a. So this element 0 is defined by this behavior. So by adding 0 to a, either from the left or from the right, we get the same a. So it has no effect on the addition. And D, for any element a, there exists an element called negative a in R such that a plus negative a is equal to negative a plus a is equal to 0. So, okay, so this is 0. And so negative a is gives an inverse operation of addition, so to speak. So by adding this element called negative a to a, we get 0. So this addition can be done from the left or from the right. Either way, we get 0. So inverse of addition. And E, for all AB in R, we have a plus b is equal to b plus a. So this means addition, this binary operation called addition, is commutative. Okay. Next, we define axioms of multiplication. So the A for all AB in R, we have AB, so this is a multiplication, is R. So this is again closure of multiplication, closure. So this set R is closed under multiplication. And B, for all A, B, C, 3 elements in R, we have A, B times C is equal to A times B, C. So this is again associativity. So multiplication is associative. So when we multiply 3 elements, it doesn't matter in which order we multiply. But it may depend on the order. I mean, okay. Uh, it depends on the way it is multiplied. So AB may not be equal to BA. So it may not be commutative. Sometimes it is commutative. In some sets, it can be commutative. In some other sets, it may not be commutative. So this is not. So AB equal to BA is not guaranteed. Okay. And also axioms of distributivity. Distributivity is a little bit strange word, but anyway. So for all A, B, C in R, we have A times B plus C is equal to AB plus AC. And similarly, for all A, B, C in R, A plus B, so add them first, then multiply by C from the right. That is equal to AC plus BC. So these are distributive laws. So if the set R satisfies all these axioms, then we say R is a ring. All together with the operations. So R, addition and multiplication is a ring, to be more precise. Let's explain these axioms in more detail. First axiom, this closure condition. Closure condition means so this ring is closed under addition. So if this doesn't hold, then if we have two elements of R and add them, and A plus B is not an element of R, then we cannot talk about addition within R. No, so R is not closed. And in that case, we're in trouble, so we don't want that. So we restrict our interest to the set such that it is closed under addition. And same for multiplication. Okay, and the second one, associativity. So it doesn't matter how we add three or more elements. So that's what associativity means. So first we add A and B, then to that we add C. That result is same as first we add B and C, and to which we add A. So in this case, it doesn't matter which one we add first. So in that sense, we can write these sums as just A plus B plus C without any parentheses. Okay. And next, the existence of zero. So this zero, although we use the same symbol as the number zero, this is just one element, any element that behaves like this. Okay, if we could have written this as, for example, alpha. So A plus alpha is equal to alpha plus A is A. If alpha satisfies this equation, then this alpha, this specific element, can be also called as a zero. But this zero is actually unique, because if there is another element that behaves this way, let's call it 0 prime. So if 0 and 0 prime are elements of R, of the ring, and they behave the same way. So 0 plus A is equal to A plus 0 is equal to A for all elements of R, A. And 0 prime plus A is equal to A plus 0 prime is equal to A. Then, since these equations hold for any element A, so A could be 0. So if we set A equal to 0, then apply the second equation. We have 0 prime plus 0 equals to 0 plus 0 prime equals to 0. Okay, and if we put A equal to A prime, 0 prime, and apply the first equation, we have 0 plus 0 prime equals to 0 prime plus 0 equals to 0 prime. So this is equal to this, and of course this is equal to this, so 0 is equal to 0 prime, necessarily equal to. So if we have two such elements, they must be identical. So this means there is only one element that satisfies this equation, if there's any. And next, regarding the inverse of addition. So for every element in the ring, there exists a corresponding element which we call negative A, such that adding them will result in 0. But we have just seen that this 0 is unique. And from that fact, we can conclude that the negative a is also unique. Okay, so that means this negative a is, it has nothing to do with negative numbers or anything. So it's just a symbol. Okay, so for every a there is another element called a negative a. So we could have just expressed the same thing by some other letters like a prime or a double prime. So these are defined in terms of how they behave. Okay, so a and a prime is equal to a prime plus a is equal to 0. If this is the case, then a prime is called the inverse, additional inverse of additive inverse of a. Okay, so suppose if there are two such elements, so behaving in exactly the same manner, then what happens? Okay, so we have this. So that means a prime is equal to a prime plus 0. So adding 0 doesn't change a prime, so we can use this equation. But 0, according to this, is equal to, let's say, a plus a double prime. But by the associativity, we can shift these parentheses, so a prime plus a and plus a double prime. But since a prime is the an inverse of a, so the result is 0 plus a double prime. But adding 0 to a double prime doesn't change a double prime. So after all, we have a prime equal to a double prime. Therefore, the additive inverse of a is unique. Okay, so, and that's one thing. And another thing to notice is that the inverse of an inverse is the same element as the original element. So we have a plus negative a. So this is additive inverse of a is equal to negative a plus a. So this means a is the inverse of negative a. So that means a is equal to the inverse of a. So if we have one element a, then its inverse of inverse is same as a. And also by convention, so if we have two elements a and b, and for each of these we have a negative a and negative b, so they're additive inverses. And if we add a and the additive inverse of b, then by convention we write this as a minus b. So we don't have to define subtraction per se. Okay, it's just an abbreviation or shorthand notation for adding two elements, and one of which is actually an inverse of some other elements. Okay, so subtraction is just another way to write an addition. And next, commutative law. So a plus b is equal to b plus a means the order of addition doesn't matter. And also, then let's see multiplications. So this is again closure. So if a and b are elements of R, and if their product is not an element of R, then we are in trouble. So we don't So if we are dealing with the ring, then we assume it is closed under multiplication. And for associativity, it's the same thing. So first we multiply A and B, then to that we multiply C from the left, from the right. Then the result is same as first we multiply B and C in this order, and to which we multiply A from the left. So this shows associativity. So instead of writing like this, since the order in which we apply the multiplication doesn't matter, so we could just write this as A, B, C without parentheses. Okay, and finally the axioms of distributivity. So these two distributive laws connects addition and multiplication together. So since a multiplication may not be commutative, so that means AB may not be equal to BA. So we are not assuming this explicitly. So we need these two distributive laws. Now, you should check that the set of integers, so the set of integers with usual addition and multiplication as numbers is a ring. And also the set of polynomials or in X of rational numbers with addition and multiplication as we have defined before is also a ring. So these are rings. So if we can prove something about rings in general, then those theorems will be applicable to both of these sets simultaneously. So we don't have to deal with them individually. So that's a nice thing about abstract algebra. And of course, there are many other examples of ring. Let's see some of them. Okay, one example is let X be a set. So this is an any set. And let R be the set of mappings from X to real numbers. So this is just a set of all functions from any set to so any fixed set to real numbers. Then we define addition and multiplication or of this set. Okay, so suppose F and G are elements of this, then we define the addition by this. Okay, so F and G are functions. And here on the left hand side, F plus G is the addition between two functions. Okay, so we are trying to define this addition by the right hand side here. So the right hand side, f of x is a real number. Okay, so this is a real number, and g of x is a real number. Therefore, this addition, f of x plus g of x, is just an addition of real numbers, just ordinary addition. So by this equation, we define a new function called f plus g that maps each of elements in x to this real number. So by this way, we define the addition between two functions. And we also define a multiplication of two functions, f dot g of x, which is defined by f of x times g of x. Again, here the right hand side is just a multiplication between two real numbers. So this is well defined. On the left hand side, f dot g is a new function defined in terms of two given functions. So this multiplication is defined in terms of the right hand side. So this way we can define addition and multiplication, and this set of functions together with these binary operations, addition and multiplication, this is a ring. Okay, and you should check this indeed satisfies all the axioms of the ring. Okay, so let's prove that this is indeed a ring. To do that, we just need to check all of the axioms. Okay, first the axioms of addition. So that is if f and g are elements of R, so f and g are functions from x to real numbers, then f plus g is also a function from x to real numbers, right? According to this definition. Therefore, f plus g belongs to R. Okay, so the closure condition is satisfied. So that is A. And next, we'll check associativity. We want to prove that f plus g plus h, of course f, g, h are all elements of R, is equal to f plus g plus h, right? So how we can prove this? So since these additions are defined in terms of additions of real numbers, we apply this definition. So f plus g plus h, if we apply this function, this is a new function, right, to an element of x, then by definition of this addition, we have f plus g of x plus h of x, right? So we have actually two functions here. One function is f plus g and another function, the other function is h. So by applying the definition of addition here, we get this. However, we still have addition here. So this, again, we apply the definition and we have f of x plus g of x. Okay, so now this is just an addition of two real numbers. F of x is a real number and g of x is a real number and h of x is a real number. So we can apply the associativity law of real numbers to have f of x plus g of x plus h of x. But by the definition of addition between two functions, this turns into g plus h of x. And again, we apply the addition of two functions, f and g plus h. So g plus h is another function. Then we have f plus g plus h of x. So this equation, it's satisfied for all elements of x. Therefore, we must conclude that f plus g plus h is equal to f plus g plus h. Okay, so the associativity of addition is proved. And next, we want to find that zero element. So what is a zero element in this case? Let us write as zero element. So this zero is a name of a function that behaves as the zero element of the set R. So let's define this function as this. So zero oh, sorry, this is a little bit confusing. So this one, on the right hand side, this is a real number. So 0 as a real number. On the left hand side, this 0 is 0 as a function. Okay, maybe we should use another symbol for that. So let us define a function z by this. So this is a function that returns a constant value for any elements of x. Then we show that this function behaves as the 0 element of this ring. Okay, so let's see. To check that behavior, so that means f plus z is equal to z plus f is equal to f, right? We need to check this equation. To check that, we apply this function f plus z to x. So by the definition of addition, we have f of x plus z of x. But by the definition of this function z, we have f of x plus 0. But this is just the addition of real numbers, so this is just f of x, right? And of course, this is equal to 0 plus f of x. Again, this 0 is just a real number, but this 0 is equal to the value of function z. And by the definition of addition, we have z plus f of x. Therefore, we do have this. So this function z, let's rename it as 0 of x, is the 0 element of this ring. Okay, and next, we need to find the additive inverse for each element. So suppose f is a function, and let's define another function. So for this function, define negative f of x by negative f of x. So here, on the left hand side, we are defining a new function called negative f. On the right hand side, this is just a real number. Okay, so f of x is a real number, and multiply that number by negative 1, and we get negative f of x. So this is just a real number. So we define this function, negative f, by this, and show that this function behaves as the additive inverse of f. Okay, to see that, we consider this. Okay, so by the definition of addition, this is f of x and this, and by the definition of negative f, this is negative f, which is 0. And also we can show the opposite also. Negative f plus f of x is zero. So this new function, negative f, is indeed behaves as the additive inverse of f. So for every element f, there is its additive inverse. Okay, and what's next? Commutativity. So we need to show is commutative. And I will just leave this as an exercise. This should be easy. Now, now about multiplication. We need to show that if f and g are elements of R, then f dot g also belongs to R. I think this is almost trivial from the definition of multiplication, right? So that was the first axiom of multiplication. And the second one is about associativity. We need to show that if we first calculate f dot g dot h, then that function should be equal to f dot g dot h. So again, this can be proved by applying this function on the left-hand side to any element of x, and just by applying the definitions of multiplication, eventually we can show the right-hand side is derived. And also distributive laws. We need to show that f dot g plus h is equal to f dot g plus f dot h. So just apply the definition over and over, and I hope this is easy to see. And similarly, we need to show that this one holds. So these are exercises and you should try. Now let's consider some more properties about integers. Okay, one thing that is not included in the definition of the ring, but present in integers, is the existence of the element 1. Okay, so the number 1 has the following property. For any element, for any integers, we have 1 times a is equal to a times a. 1 is equal to a. So this is like so in the case of addition, we had the unique element 0, and this element 1 behaves much like that 0, but instead of addition, it applies to multiplication. And second property is that in integers, multiplication is commutative. So for any element a, b, which are integers, we have a times b equals to b times a. It's commutative. And the third property is that if a and b are non-zero, then this means a implies a times b is not 0. These three properties look so trivial that we don't pay much attention usually, but they do deserve some attention. So these are very special properties, but they are so important that we give some definitions for them. Okay, so let's define this. Let R be a ring. So this means this is a set equipped with addition and multiplication, and that satisfy all the axioms required for a ring. Okay, then first an element 1. So this 1 is not necessarily the number. So this is just a symbol. Okay, any element that satisfies the following property. 1 times a equals to a times 1 equals to a for all elements of R. Okay, so such an element, such that element is called an identity element, or simply identity or unity. Of R. Okay. So any element that behaves like this, so multiply with any element either from left or the right, yielding that same element, so without no effect. Such an element is called an identity element, or identity or unity. And second, let's say A, B are elements of R, then if AB is equal to BA, then we say A and B commute. We say A and B commute. And if this this commutativity holds for all pairs of elements in R, then we say the ring is a commutative ring. Okay, so if for all elements AB, AB is equal to BA, then we say R is commutative. Or R is a commutative ring. And 3, let 0 be the 0 element of R, and let A be elements of R such that AB is equal to 0. Then A and B are called divisors of 0. If okay. So if A times B is equal to 0, A and B are divisors of 0. And if both, okay, so this is one thing. And furthermore, if A is not 0 and B is not 0, so either of them is not 0, but still AB is 0, then we say A and B are proper divisors of 0. Of 0. Okay, it may, if you just consider integers, this may sound strange, because if two integers are not 0, their product is never 0. But for some rings, this can happen. So therefore, we give it a name. So it's a proper divisors of 0. And for the identity element, we can say that if there is any identity element, it must be unique. So just like the uniqueness of 0 element of a ring, if there is an identity element of multiplication, then it is also unique. So let's say if 1 is an identity element and 1 prime is also an identity element. So that means for all elements of R, we have 1 times A is equal to A times 1 is equal to A, and 1 prime times A is equal to A times 1 prime is equal to A. So if this is the case, then we can show that this 1 is actually equal to 1 prime. So try to prove this. Therefore, the identity element is unique. And here's another definition. Okay, so a commutative ring with an identity element, identity element 1, which is not equal to 0. No, it can be the case that the identity element is equal to the 0 element. But anyway, if that's not the case, and no proper divisors of 0. Is called an integral domain. So this is the definition of an integral domain. It is a ring in which multiplication is commutative for all pairs of elements, and it has an identity element 1 and no proper divisors of 0. So that means if a product of two elements is 0, then either one of the elements must be 0. So that's what this means, no proper divisors of 0. So if that's the case, we call that ring an integral domain. An integral domain is a ring that behaves much like the set of integers. So this integral refers to integers. Okay, let's prove some theorems. This theorem is almost trivial, pretty trivial for integers, but we need to prove this for general rings. So let R be a ring. So again, this is a set equipped with addition and multiplication satisfying a certain set of axioms. Okay, first, for A, B, C, which are elements of R, if A plus B is equal to A plus C, then B is equal to C. And if A plus B is equal to C plus B, then A is equal to C. And second, for all A elements of R, A times 0 is equal to 0 times A is equal to 0. So multiplication by 0 gives 0 for any elements. And 3, for all AB in the ring, we have A times negative B is equal to negative A times B is equal to negative AB. And also negative A times negative B. So, this negative A and negative B are additive inverses of A and B respectively. Okay, and this is equal to AB. And if R has an identity called 1, then negative 1 times negative 1 is equal to 1. And for all AB in R, A times B minus C is equal to AB minus AC, and A minus B times C is equal to AC minus BC. So we're going to prove this. Okay, let's prove this. First, this one. Let's see. So, this one, A plus B is equal to A plus C implies B is equal to C. So we want to prove this, but please be careful. We cannot just cancel the same elements from the right hand side and the left hand side, because we have not defined what that means. Okay, canceling is not defined in the axioms or anything yet. Actually, this theorem ensures that canceling is okay. Okay, so let's see how we can do this. So suppose we have A plus B equal to A plus C. Then we add both to the both sides negative A. Okay. So this is okay. We are just adding some element to both sides, and they are still equal. And then using associativity of addition, we have negative A plus B and plus C, and we have 0 plus B and 0 plus C. And by the property of 0, we have 0 plus B is B, and 0 plus C is C. And we are done. Okay, and the other equation, what was it? So A plus B equal to C plus B implies A equal to C can be proved in the same manner. So adding negative B to the both sides. And next, second, what was it? So multiplying by 0 either from the right or the left gives 0. Okay, so first of all, A times 0 plus A times 0 is equal to, so using the distributive law, we can factorize A out. So 0, A times 0 plus 0. But by the property of 0, adding 0 doesn't change 0. So that is A times 0. Okay, and this is equal to, again using the property of 0, A times 0 is equal to A times 0 plus 0. Okay, now we have this equals to this, and we have the common element A times 0 here and A times 0 here. And using the previous result in part 1, we can cancel the same elements from both sides. So this means A times 0 is equal to 0. And we can prove similarly that 0 times A is equal to 0 in much the same manner. And next, let's see, part 3, we want to prove a times minus b is equal to minus a times b is equal to minus ab. Let's try this one first. Let's try to prove this. Okay. Just ignore this one for a moment. Just try to prove this equals to this. Okay. And let's see. First of all, we have AB plus negative AB equals to 0. Now, this is the definition of the additive inverse. So, the additive inverse of the element AB is negative AB. Okay, so this is just from the definition of the additive inverse. And so this is one thing. On the other hand, let's see. We have 0 equals to a times 0 from part 2. But 0 is equals to b plus b plus minus b, right? b and its additive inverse, if we add them, it's 0. So we have this equation. And now use distributive law. We have ab plus a times negative b. Okay. So we have two things that are equal to 0. One, this one, and the other one is this one. So that means this AB plus minus AB is equal to AB plus A times minus B. So let's write it down, and therefore AB plus A times negative B is equal to AB plus negative AB. But here we have AB here, AB here. So according to part 1, we can cancel the same elements. Therefore, we have A times minus B is equal to negative AB. And we are done. And we can prove the second part in a similar manner. So instead of this one, instead of expanding b in this way, we can find 0 is equal to 0 times b and such and such. I think you can guess. Okay. So by proving the similar thing in a similar manner, we have negative a times b is equal to negative of ab. So these are of course equal. Okay. Now let us write a prime to represent negative a, just for simplicity. So from this, we have negative a prime is equal to negative of negative a. But we have seen that this is actually equal to a, right? So, so from here, we have negative a times negative b is equals to, so by definition of a prime, this is a prime times negative b, but using the previous part here, this is equal to negative a prime times b. But negative a prime is a, so this is equal to ab. And we are done with this. And then if we have the identity element in the ring, then by applying this, we have negative 1 times negative 1 is equal to 1 times 1. But from the property of the identity element, 1 times 1 is equal to 1. So we are done with part 3. And part 4 should be straightforward. once you recognize the definition of subtraction. So a times b minus c. This really means a times b plus minus c, right? This subtraction is just an abbreviation for this addition with an inverse element. Okay, then we apply the distributive law. So that becomes ab time plus a times negative c. But from part 3, we know that a times negative c is equal to negative of a c. But we can abbreviate this operation as ab minus ac. And we're done. And we can prove in a similar manner that a minus b times c is equal to ac minus bc. Okay, so this is an exercise. Let's see an example. This time, suppose D is an integral domain. So it's a ring with some additional properties. Then suppose A, B, C are elements of D, and also assume that D is not 0. And suppose AC is equal to BC. Then we want to prove that we can cancel this C. So in the previous theorem, it was we could cancel the same terms in addition, but in this case we can cancel the same terms factors on the both sides in multiplication. Okay, so from this AC equal to BC. So if we add negative BC to the both sides, we have AC minus BC equals to 0. And using the distributive law, we can write A minus B times C equals to 0. Now, we are assuming that D is an integral domain. So there are no proper divisors of 0. So this means, so A minus B times C equals to 0 means A minus B is 0 or C is 0. But by assumption, C is non-zero. So this is not the case. So only this is possible. And by adding b to the both hands, we have a equals to b. So after all, we can cancel this c to have this equality. And so far, as for polynomials, we've been considering something like polynomials over integers, or polynomials over rational numbers, polynomials over real numbers, and so on. But so these Z, Q, R, they are some specific set of numbers, but more generally, we may be able to think something like this. So it's a polynomial over some integral domain. So let us assume that D is an integral domain. So this is any integral domain. It may be an integer, but it may be something else. And we may be able to talk about this kind of polynomials with all coefficients being an element of this integral domain D. So Then we have the following theorem. Okay, so let D be an integral domain. And then the polynomial ring, as we've seen, polynomials make the set of all polynomials make a ring. Then is then d of x, the set of all polynomials in x over d, is also an integral domain. Okay. Now let's prove this. Now I think it's clear that this polynomial ring is a commutative ring. With the identity. With an identity, maybe. Identity. So what is this identity element in this polynomial ring? So that is a function, 1 of x, that is equal to 1. So it's a constant function. And this 1 is an element of this underlying integral domain. So if we define the function like this, 1 of x as a constant function, then this behaves as the identity element of this polynomial ring. And about this commutativity, since D is an integral domain, all coefficients, like so if we have two polynomials like this, and bx, bn, xn, then so for all coefficients like ai times bj, since ai and bj are elements of this integral domain, they are commutative. So bj, ai. So if we multiply these two polynomials, we always have this b of x times a of x, because we can commute every product like this. So this holds. Therefore, this polynomial ring is a commutative ring with this identity. Okay. Then to show that this polynomial ring is an integral domain, the only thing that is left to show is that this ring has no proper divisor of 0. Okay, so let's assume these polynomials with am not equal to 0, bn not equal to 0. So the degrees are m and n for this. Then f of x times a of x times b of x has the highest term, so that is am times bn times x to the power of m plus n. And d, since d is an integral domain, and we're assuming am and bn are non-zero. Am times bn is non-zero. D doesn't have proper divisors of 0, so this cannot be 0. So this means this product a of x times b of x is non-zero. Therefore, this means this polynomial ring has no proper divisors of 0. Therefore, d of x is an integral domain. And we are done. And as a corollary to this theorem, by the way, corollary is a small theorem that can be very easily derived from another theorem. So from this theorem, we have if a of x and b of x is, and if they are polynomials in this polynomial ring of over integral domain, then degree of a of x times b of x. So the degree of this product is the sum of degrees of the two products, two polynomials. The proof is actually already contained in the previous proof. So these are the polynomials, two polynomials with degrees m and n. And since the degrees are m and n, these coefficients are non-zero. So if we take the product, the highest term is this, and the degree is m plus n. And of course, since it's integral domain, am and bn times bn is non-zero. So indeed, the degree of the product polynomial is m plus n. In the case of set, we can define the notion of subsets. So for example, if we have a set, then we may have a subset. In a similar manner, we can define the notion of subring. And as you can guess from this name, subring is a subset with the ring properties. Okay, so here's the definition. Suppose R is a ring, and S is a subset of R, which is non-empty, and also S is a ring with the same addition, same binary operation, addition, and multiplication. Addition and multiplication, they are not unique. So we may be able to define different types of additions and multiplication for any types of any sets. But here we are saying that R is a ring, so it comes with some addition and multiplication. And S is a subset of R equipped with the same addition and multiplication as R. Okay. Then we say S is a subring of R. Okay, this is the definition of a subring. So basically, subring is a subset of some ring, which is also a ring with the same binary operations as R. Now, given a subset of some ring, so let's say we have a ring R, and let's say we have a subset of R, which is non-empty. Then in order to check whether this subset is a ring or not, in principle, we need to check all the axioms for this ring, this subset S. But in practice, we don't have to do that. We only need to check only a few axioms. So that is called, it's a theorem called the Subring criterion. Yeah, here it is. So we assume R is a ring with some addition and multiplication defined, and S is a subset of R, and it's non-empty. Then S is a ring, a subring actually, subring of R if and only if the following three conditions are met. That is the axiom 1a, that is S is closed under addition. So this addition is of course the same addition as R. And the second, maybe I should write 1.d for all A in S. So for each element of S, its additive inverse within R is actually an element of S. Okay, so this additive inverse of A is originally defined within R. So its existence within R is guaranteed. But if that element happens to be an element of S, this subset S, then this condition is met. That's what this means. And the last condition is that S is closed under multiplication. Multiplication. Of course, this multiplication is the same multiplication as in R. So, if these three conditions are met, then S is a subring of R. And if S is a subring of R, then these three conditions are met. So this is if and only if relation. Now, let's prove this theorem. So in order to prove if and only if type of theorem, we need to prove both directions. First, proving only if part. So if S is a subring of R, then these three conditions are met. This is easy. Since suppose S is a subring of R. So basically S is a ring. So since S is a ring, it satisfies all the axioms, all the ring axioms, which includes these three. So we are done. The if part, this is more involved. Okay, suppose S satisfies the above three axioms. So this, this, and this, and this are satisfied. Okay, what we need to show is that we want to show S is a ring. Okay, so given that S is a subset of R and these three conditions are met, we need to show that all other axioms are also satisfied. So that's the basic strategy for this proof. But that's actually tedious but straightforward. So I will skip some of them, most of them actually, and prove some of them only. Okay. For example, the axiom 1.c. Uh, let's see. For all element in S, then by the requirement, by the assumption, negative S is an element of S. So that means, but S is closed under addition by this condition. So A plus negative A, so this should be an element of S. But within R, A plus negative A is 0. So this element 0 must be an element of S. So that proves the existence of 0 element within S. And what about the axiom 1b? That is the associative law for addition. So for all A, B, C in R, we have A plus B plus C is equal to A plus B plus C. Okay. Therefore, for all A, B, C, if they are elements of S, and because of this, since S is a subset of R, of course we have A plus B plus C is equal to A plus B plus C. Since S is a subset of R. So therefore, the associative law is satisfied. And similarly, all other axioms should be proved. I will skip the rest and just finish the proof here. Let's see a few more examples. Okay, the first example, this M2 of Q. So this is the set of all matrices, all 2 by 2 matrices with rational numbers as elements. Okay, this is actually a ring with usual addition and multiplication of matrices, and you should check that. And so so this is a ring. So this is a ring, as you can easily check. And another example. So let's consider a subset of this set of matrices, 2 by 2 matrices. So let's define this set S by the following. So this is the set of matrices of this form, X, Y, 0, and Z. And X, Y, Z are rational numbers. Okay, we claim that this set of matrices with one element being 0 here, 1, 2 element being 0, is a subring of M2Q. Okay, let's check that. According to the subring criterion, we need to check 3 conditions. Okay, first, this should be closed under addition. So let's say we have X, Y, 0, Z. This is one matrix element of S. Another matrix, maybe like U, V, 0, W. So if you add this, we have X plus U and Y plus V and 0 and Z plus W, which is an element of S, obviously, because this element is 0. Okay, so the first condition is met. And the second condition is the additive inverse a member of this subset. So negative of this matrix is negative x, negative y, 0, negative z. And of course, negative x, negative y, negative z, they are all rational numbers, as long as x, y, z are all rational numbers. So therefore, this matrix is an element of the set S. So the additive inverse is always included in S. And the third condition, what about the multiplication? Is this subset closed under multiplication? So consider this UV0W. So usual matrix multiplication. So x times u and y minus 0 is 0, and x times v yw 0u plus z0 is 0, and 0v times zw is zw. Again, this is an element of S because this element is 0. So all three conditions are met. Therefore, this set is a subring of this ring. Let's see a few more simple examples. A very simple example is this. The set R consisting of only one element, 0. And so this is just a, this is not necessarily the number 0 as in the usual case, but this is just a symbol. Okay, and we define addition and multiplication by this. So since there is only one element here, 0 plus 0 must be equal to 0. And 0 times 0 must be equal to 0. So this is the definition of addition and multiplication. Then, under these operations, this set R is a ring, and you should check whether that is true. So actually we can consider this as a subset of integers. So we just regard this 0 as the usual number 0. So in that case, this is true for integers. 0 plus 0 is 0, and 0 times 0 is 0, just like in integers. So you may check the subring criterion for this and see that this is indeed a ring. That's one example. And another example, a little bit more complicated, but now we have two elements, 0 and 1. And we define addition and multiplication by the tables, the following tables. So for addition, so this table is read like this. So 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. And 1 plus 1 is 0. So this is just a definition, okay? So the rule of the ordinary integers does not apply. About the multiplication, 0, 1, 0, 1. So 0 times 0 is 0. 0 times 1 is defined to be 0. 1 times 0 is 0. 1 times 1 is 1. So if we define addition, and multiplication in this way, then this set R is a ring. Not only just a ring, it is actually an integral domain. So you need to check that this is a ring, and in addition, you need to check some more conditions for integral domains, like existence of 1 and commutativity of multiplication and absence of proper divisors of 0. Okay, that's it for today.